Okay, so we're going to look at a neat way of multiplying integers by 7. I think this makes a lot more sense when we see it with an example, but just very quickly, the steps involved are we start at the right hand side, so we start with our units column, we take that digit, we would double this, then we'd add half of its neighbour to the right, rounding down if we have something that's not an integer, and then if that original digit we were working with was odd, we'd need to add 5 to that. Then finally at the end of this process you would add in anything that perhaps needed to be carried over from the previous digits. Then you keep working, going from the units column to the tens column to the hundreds and so on. So let's look at this with an example. Let's do 5,432 times 7 following this method. So we start on the right hand side, we've got this 2 in our units column. First thing we do is double this, so we get 4. Then we add half of its neighbour to the right. So the neighbouring digit to the right of this is just a 0 in the tenths column, so there's nothing to add there, so we're just adding 0. Then if this 2 was odd, we would need to add 5, but because it's even, we don't need to do any addition there. And finally, there's nothing left to add from any of the previous steps, so we're just left with a 4 in our units column after this first step. So now let's go on to the 3 in the tens column. So we double this first of all, we've got a 6. Then we add half of its neighbour to the right. So its neighbour to the right is this 2, so we add half of 2, we just add 1 here, and then we've got a 7 in our tens column. And now the original digit 3 is odd, so we need to add 5 here. So we're going to get 12, which we'll write as 2 with an extra 1 that needs to be carried. And finally, there's nothing left to carry from the previous step, we've just got this 4. So we've effectively got 24 now with this extra 1 to go into our hundreds column after these two steps are complete. So now let's have a look at this 4 in our hundreds column. We start by doubling this 4, which gives us 8. We add half its neighbour to the right, so half of 3 is 1.5. But here we actually round down to just add 1, so that we're working with integers. So we're only adding 1 here, so we've got 9 now, after doing half of 3 rounded down, adding 1 there. And then this 4 is even, so we don't need to add 5. And then finally we've got this extra 1 which needs to be carried. So then instead of having 9, we've actually got 10. So we'll write this as 0, 2, 4. And we've got an extra 1 to carry into our thousands column for this final step. So for our final step now, we've got 5. We need to double this, which gives us 10. So we'll write this as 0 with an extra 1 to carry. And then we add half its neighbour to the right. So we add half of 4, we add 2. So we've got a 2 there, and the original digit is odd, so we do need to add 5 here, so we get 7. And then finally we add anything that was carried from the previous step. So here we've got this extra 1, so we add this to the 7, giving us an 8. So we've got 8, 0, 2, 4, plus this extra 1 at this final step. But of course 8024 isn't the final answer to this. And what's missing here is when we're working with this method, we effectively need to think of the leading digit being a 0 here, so that then we can still do this step of adding half of the neighbour to the right, so that this algorithm will then terminate. So thinking of this 0, we double this, we've just got 0, but then when we add half of the neighbour to the right, half of 5 is 2.5, which rounds down to 2. So we need to add an extra 2 to this 0. And then the original digit 0 isn't odd, so we don't need to add 5. And then this allows us to finally add this extra 1 that should have been carried from the previous step. So this gives us 38,024, which you can check is indeed the value you should get when you do 5,432 times 7. So now let's try to understand why this method works by taking a closer look at exactly what we've just done with all of these steps. So we had 5,432 times 7. So focusing first of all on the 2, all we did with the 2 was double it, so we had 2 times 2, but then later on when we were working in the tens column we added half of the neighbour to the right, so we effectively took this 2, put it into the tens column, so we had 10 times 2, but then we also halved this, so this gives us a net result of having 5 times 2. So this is quite a nice way of seeing that we have 2 times 2, but then by adding half the neighbour in the next column, we also get a contribution of 5 times 2. Then when we look at the 3 in the tens column, this is a little bit more complicated. So the 3 in the tens column, we doubled this, which I'll write as 2 times 30, because the 3 really represents a 30 there. But then we also had this step where, because 3 is odd, we add 5 in the tens column. So we also add 50 here. And finally, when we were working in the hundreds column, we added half of this neighbour, so half of this 3, rounding down. So we only actually added, instead of adding 1.5, we added 1 in the hundreds column, so plus 100. But you can see here the net result of having the plus 150 and the plus 100 is the same as having plus 5 times 30. So we do still have this contribution of 2 times 30 and 5 times 30. So we have really multiplied this 3, representing the 30 there, by 7. We've just got this extra step where, in order to make sure that we're working with an integer in the hundreds column, we round down, and to counteract that we added this extra 5, which was worth 50, because we're in the tens column there. So now if we go on to the 4, which is worth 400 there, this one was a little bit more straightforward because it's even. So we had 2 times 400, and then we also took half of this into the thousands column. So we also had plus 10 times 400 divided by 2, which is the same as adding 5 times 400. So you can see there we get 2 times 400, and we've also got 5 times 400. So we have added 7 times 400. And then finally for our 5 here, we double this. We've got 2 times 5,000, because the 5 represents 5,000. But then we had this extra added step where we added 5 here, so we're plus 5,000 because we're working with an odd number. And then when we were adding into this 10,000s column, half of this 5 rounding down, we ended up adding effectively 20,000. So instead of adding 2.5, we only added 2 into the 10,000, so we added 20,000 there. And adding 5,000 and 20,000 is indeed equivalent to adding 25,000, which is 5 times 5,000. So then you can see we've really added 7 lots of 5,000 there. And then this extra step at the end where you just carry everything from the previous digits is how we add all of this together. So that takes care of the addition. You can see here we really have just taken all of our different digits there and multiplied them all by 7. And now let's finish with a slightly more formal proof that this method works for any integer multiplied by 7. So we have a general integer where we've got a0 in the units column, a1 in the tens column, and so on all the way up to an in the 10 to the n column. We multiply this by 7. We'll see how this method works by, first of all, let's write all of these digits in terms of their place value. So we've got 10 to the n times an plus 10 to the n minus 1 an minus 1, and so on all the way down to, it would just be 10 to the 0, or just 1 times a0, and this is all being multiplied by 7. So let's write this sum now using sigma notation to make this a bit easier to work with. So we can write this as the sum going from k equals 0 up to n of 10 to the k multiplied by the digit ak. And because we're multiplying this by 7, we're actually going to break this up into a sum where we multiply this by 2, then we also multiply the same sum by 5. So you can actually see, perhaps to begin with, this first term is starting to reflect our initial step in our procedure from earlier of just doubling our original digits. You take all of your digits and just double them. So we can label this double the digit, and we can see where this first step in our procedure came from. But now let's have a look at this where we've got 5 times our original sum. We're actually going to write this 5 as 10 and divide by 2, and we'll take this inside the sum. So if we just take, we'll leave our first sum alone, going from k equals 0 to n of 10 to the k ak, but then when we get to this term, we'll turn this 5 into a 10 divided by 2, and we'll also take this inside the sum. So we've got the sum from k equals 0 to n of, instead of 10 to the k, it becomes 10 to the k plus 1, and instead of ak, we have ak divided by 2. So we've multiplied by 10, but we've divided by 2 to cancel this out. So now, at this point, you've got 10 to the k plus 1, and you've got ak. So we're actually going to re-index this sum. Let's just introduce a new letter, a new variable r, which is k plus 1. So then this is going to allow us to write our sum as the sum going from r equals 1 up to n plus 1, rather than just up to n. And then we've got, because r is k plus 1, it's 10 to the r, and then k is r minus 1, so ak becomes ar minus 1. This still all gets divided by 2. And we've still just added the original sum there as well from k equals 0 to n of, this is just double our original number we were working with there. So now we've got this new sum here. We've got 10 to the r times ar minus 1 divided by 2. So we're starting to see some of this structure emerge of adding half of the neighbouring digit to the right. And you can also see, because the sum goes up to n plus 1 now, why we would need to add in that 0 at the beginning. So before this an here, we'd really need to add in a 0 just for that very final step. But there's still some more work to be done to see what happens here with this rounding down and also adding 5. And a nice way to make this work is just to actually split this sum up into the sum where ar minus 1 is odd and also the sum where ar minus 1 is even. So this gives us a nice way of seeing the two different cases where we either add 5 and where we have to round down. So if we write this, first of all, we've got the sum from r equals 1 up to n plus 1 where ar minus 1 is even. So we'll just leave this alone. We have 10 to the r times ar minus 1 divided by 2. So this is the nice case where ar minus 1 divided by 2 is still an integer, so we can still work with this in terms of place value, and that's nice to work with. But then we also need to split up into the portion of the sum, again going from r equals 1 up to n plus 1, but only including the ones where ar minus 1 is odd. So these are the ones which are difficult to work with because ar minus 1 divided by 2 is no longer an integer, and at this point we need to actually round this down in order to work with it. So rounding this down, as we saw with our examples before, let's say we had 2.5 rounded down to 2, we always just need to take away a half there. And to counteract this, we'll also add a half, which we can then deal with later. So we'll do some more manipulations to this sum, and then we'll see why our original method does indeed work after some more calculations. So here we've got the sum of the odd digits. We're actually going to split this up into two separate sums now. So we'll write this as the sum from r equals 1 up to n plus 1, ar minus 1 is still odd, and we'll just take the first two terms in this bracket. So we've got 10 to the r times ar minus 1 over 2 minus a half. So we've got this term, but then we also need to have this plus a half term, so we've got plus the same sum going from r equals 1 to n plus 1 where our digits are odd, and we've just got 10 to the r times a half. And for this remaining sum here, we're actually going to re-index this so that we go back to our original variable k. So if we introduce again now k is equal to r minus 1, so then this whole sum here becomes the sum going from k equals 0 up to n of, we've got 10 to the r, which is 10 to the k plus 1. So we'll write this as 10 to the k multiplied by another 10, but then we've also got multiplied by a half. So this is just being multiplied by 5 here, and we're still summing over where ar minus 1 is odd, so r minus 1 is k, so this is ak is odd here. So this explains where we get this extra plus 5 for all of our odd digits, and then we can add in the remainder of all of these sums. So we've also got this where ar minus 1 is odd here. We've got the sum going from r equals 1 up to n plus 1 where the digit is odd of 10 to the r times ar minus 1 over 2 minus a half. So this is effectively where we have an odd digit, we need to subtract a half to round this down, and we can also add in the other two previous parts of the sum. So we've got here plus the sum of 10 to the r minus 1 over 2 where r goes from 1 up to n plus 1 and the digit ar minus 1 is even. And finally we've also got this original sum, and I'll take the 2 inside here, so we'll write this as the sum going from k equals 0 up to n of 10 to the k times 2 times our original digit ak there. So now this is a really nice way of seeing the original multiplication by 7 split up into lots of different sums. So this first sum here is just where we double the digit, so we can label this double the original digit. And then for our second two sums, split up into the case where we've got an even digit or an odd digit. There should be a plus sign there as well, and there. So for these two sums here, we're effectively just saying we add half of the neighbour to the right for this step, so add half the neighbour. And we also include this nuance now of subtracting a half when we have an odd number. So this includes the nuance here of rounding down if we have an odd number divided by 2. And then this very final step here is where we add 5 to the digit if our digit was odd. So this is a really nice way of seeing then that doubling our original digit, adding 5 if it's odd, then adding half of the neighbour to the right, rounding down, does indeed give us our original number multiplied by 7 after doing all the carrying for all of the addition there.